All right, let's take a look at Unit 5, Lesson 9, Scaling the Inputs. So every weekend, Elena takes a walk along the straight road in front of her house for 2 miles, then turns around and comes back home. Let's assume Elena walks at a constant speed. All right, so here's a graph of the function f that gives her distance in miles from her house as a function of time t as she walks 2 miles per hour. All right, so when the time starts, she's walking away from her house until she gets 2 miles away from her house. And it takes her an hour to walk that 2 miles. And then she starts coming home. And then at 2 hours, she is at home. All right, because she's walking 2 miles per hour. So it takes her an hour to walk 2 miles away from her house and then an hour to walk 2 miles back to her house. All right, so sketch a graph of the function g that gives her distance, g of t, in miles from home as a function of time, t, if she walks 4 miles per hour. So if she's walking 4 miles per hour, she is going to, let me write this down. So 4 miles per hour. So then it's going to take her half as much time to walk 2 miles. So because our graph, our grid doesn't go up to 4 miles, so we can't really graph that 4 miles per hour, but what we can do is say, okay, well, if it takes her an hour to walk 4 miles, so 1 hour for 4 miles, then it's going to be a half an hour to walk 2 miles, okay? And so it's going to take her a half an hour to get to 2 miles, and then, because she's still walking the same distance, it's just that her speed changed. So she's not actually walking 4 miles away from her house. She's only walking 2 miles away from her house, but it's taking her half the time to get there. So we're going to write an equation for g in terms of f. So g of t is equal to f of what? All right, and so keep in mind that her time is essentially cut in half. So she's doubling the output when she's walking faster. So if f of t is equal to 2 miles per hour and g of t is equal to 4 miles per hour, right? What have we done to the f of t? We have multiplied by 2, right? And so we're putting in 2t there, right? Because remember, she's reaching her maximum at a half an hour. So if I double this value, 2 times that value, I'm going to get that value. So I have to double my t when I put it into the f function. All right, let's take a look at 9.2, a new set of wheels. Remember Claire on the Ferris wheel? In the table, we have the function f, which gives her height, f of t, above the ground in feet, t seconds after starting her descent from the top. Today, Claire tried out 2 new Ferris wheels. The first Ferris wheel is twice the height of f and rotates at the same speed. The function g gives Claire's height, g of t, in feet, t seconds after starting her descent from the top. All right, and then we'll talk about the second wheel in just a minute. All right, so the first one. So the height is twice the height of f. So at time 0, that height is going to be 424 because it's twice as high, right? And then at 20, it's going to be twice that 1 181, so that's going to be 362. At time 40, it's going to be twice the 106, so that's 212. At 60, times 60 seconds, it's going to be at 62 feet. And then at 80 seconds, it's going to be at 0 feet. Okay? Now, if we want to find h of 20, okay, hold on. Let's go back. All right, so we completed the table for function g. Now let's take a look at the second wheel. So this is the first wheel. And now we're looking at the second wheel. It's the same height as f, but it rotates at half the speed. So the function h gives Claire's height t in feet, t seconds after starting her descent from the top. All right, so if we want to find h of 20, that's going to be the same thing as f of 10, but we don't know what f of 10 is because that's not on the table. Same thing for h of 60, that's going to be f of 30, because remember it's rotating at half the speed, and we don't know what f of 30 is, so we don't have enough information to be able to find those values. But we can find some of the other values because we can find half of t, right? This is going to be h of 0 divided by 2, which is the same thing, so it's 212. This is going to be, I'm sorry, that's not h, that's f. This is going to be f of 40 divided by 20. I'm sorry, 2, not 20, because the answer is 20. So that's f of 20. So whatever f of 20 was, which is 181, that's what our value is going to be. And this one's going to be f of 80 divided by 2, which is f of 40, which we do have, and that was 106. All right, so we have some of the values on the table, but we don't have all of the values on the table. So if we want to express g in terms of f, so g of t, that's going to equal, remember our output's doubled, so it's 2 times f of t. And then our h function, remember we were cutting our time in half, so it's going to be f of half of t, which you could write like that, or you could write it in decimal form if you want. H of t equals f of 0.5t. Either one is fine. All right, let's take a look at the next part, 9.3, the many transformations of a function p. So function k is a transformation of function p due to a scale factor. We're going to write an equation for k in terms of p. So let's see what is happening here. Okay, so this is function k, and this is function p. All right. So we're multiplying function k by something. So it's k of x equals something. And what kind of stretching do we see? We don't see horizontal stretching. We see the output changing. So we're multiplying the output by something, not the input. And so some of these values don't really change, but we do have this value is the 0.12, where its corresponding point is the 0.16. And so you can see that, not sure why I have that there. You can see that multiplied by 3. Let's just check another point just to make sure. So we know that this point right here is the point -1, -2. And this point, the corresponding point, is -1, -6. So that does make sense. And so we're multiplying that p of x by 3. Okay, because our output is what is changing, what is growing or shrinking. All right, taking a look at number 2, on the same axes, graph the function m, where m of x equals p of 0.75x. So basically, if we have a smaller x value being plugged into the p, it's going to be a larger x value plugging into the m. So that's kind of the same thing as m of, and this is 3/4. So 4/3 x is equal to p of x. Because it's just the reciprocal. So if you were to, because your x values, if you say, okay, so x is equal to not equal to 0.75x, but if you divide both sides by that 0.75, we'll say that's x sub 1 and x sub 2. And then, so that's going to be, that's why it becomes 4/3 x. Okay, so basically your y value doesn't change, but the x value increases by a factor of 4/3, right? And so if we look at, let's say this point, that's -3 times 4/3. So that's going to give us -4. So that's going to stretch out to here. Let's see, -2 times 4/3 gives us -8/3, which is, let's see, about -2 2/3. So that's going to be about there. 0 stays the same. This one is 1 times 4/3. So that becomes 1 1/3. And then the 4 becomes 16/3, which is about 5 1/3. So that comes right about there. And so then we just connect. So you can see that it's gotten stretched out a little bit by a factor of 4/3. All right, the highest point on the graph of P is 1, 2. What is the highest point on the graph of a function n, where n is P of 5x? And so remember that wherever x is 1 here, like if x is 1, then x here is 1/5, right? And so if we look at that value, if our P of 5x would be kind of right here, because remember your y doesn't change, so that's still the highest point. So you would have 1/5, 2 would be that highest point, because the y values aren't changing, you are stretching across the x-axis, so it would be, actually this one's smushing because it's a factor of 5. Okay, let's see. Number 4, the point furthest to the right on the graph is P of P is 4, 0. If the point furthest on the right of the graph of a function Q is 18, 0, what's a possible equation? Okay, so it's 18. So we are going from 4 to 18. So our Q of x is equal to P of something times x. And remember, we are stretching from 4 to 18, so we're looking at 4/18. 4/18 x. All right, and you can go ahead and take a look at that summary if you want to review.